Hello, welcome back to another episode of Math with Hoss. You're watching Precalculus Season 2, Episode 24. We're continuing our investigation of trigonometry, and in particular, we're going to dedicate this video to Arcsecant, Arccosecant, and Arccotangent. That's right, we're talking about the inverse trig functions for secant, cosecant, and cotangent. So, when you take a normal pre-calculus course, they don't talk about these functions. Part of the reason is because these three functions can be rewritten in terms of sines and cosines in pretty much all real-life applications. You don't really need these functions. However, I felt like it would be worthwhile to dedicate at least one video giving a shout out to these three functions, but we're not going to dive too deep into it. In part because it can be kind of repetitive deriving these equations in the same manner, like what we did for arctangent, arctangent, arccosine, and arcsine. So the basic procedure is, if you think about our normal trig functions, the inputs and the outputs are swapped, right? So if we think about y is equal to secant x, the question now is what happens when you have x equaling secant y. So that means what was the, oops, we gotta modify that a little bit. And this function where we swap the x's and the y's, we're going to denote that with -1. So when we have y equals secant x, that's our normal secant function. Now we have x equals arcsecant of arcsecant of y. That's what this -1 here represents. That is the inverse trig function for secant, which I'll usually just say as arcsecant, and that's what these here are all about. Alright, so enough about terminology. So our basic plan is pretty much whatever the x values were for our inputs for secant are now our outputs, and the corresponding y coordinates are now our inputs. And so what you would normally do is make a table of values, and I went ahead and did that for sine, cosine, tangent. We're not going to worry about that with these functions. Instead, we're going to just go straight to a graph. Thank you to Desmos. So this right here is actually the graph for just secant x, okay? So, and we got three asymptotes here, right? Secant has infinite number of asymptotes at pi over 2 plus n pi, where n is an integer, so any integer amount of pi add. So if we add 1 pi to pi over 2, we get 3 pi over 2. If we add another pi, you would get 5 pi over 2 over here. If we subtract a pi, that brings us right here, negative pi over 2. And you can add or subtract as many integer amounts of pi, and you get those asymptotes. So question now is, what happens when the inputs and the outputs are swapped? In other words, what happens when we graph x equals secant y, which is actually what the arcsecant is all about. So, intriguing. Now, if you've watched the other videos before, which I keep mentioning, and I will put the descriptions in I'll put the links in the descriptions. What we have here is, of course, we see the problems with we have our vertical asymptotes. They are now going to become horizontal asymptotes. So in fact, we switch this to a y, we get our vertical asymptotes. What were, or not vertical, but horizontal. What were vertical asymptotes before are now horizontal asymptotes. See there? So that same section of graph that we had before is now right here in between. So we can see that we need to make a domain restriction So if we make a domain restriction where x is, say, between 0 and 2 pi, let's just see what that looks like. And here's 2 pi. So that gives us partograph, and we're missing this stuff over here. So that's interesting. Oh wait, no, we want y. Okay. Yeah, let's go ahead and change this up a little bit. So 0 was insufficient, so we need to go negative pi over 2. 3 pi over 2. There we go. Alright. So before, when we had just secant, let's turn these off for a moment. So when we think about secant, x was from 0 to 2 pi, or from 0 to 2 pi, that gave us kind of one whole period of the graph. Now we're just going to think about changing it slightly. We want to consider it in terms of y now, since y is now the input, so our outputs and inputs get switched, as we said before. So we're just considering this part here, and that is just as the first two u's. So that's this u shape here and this u shape here. Alright. Now, without that domain restriction, we saw all these sideways u's, and now the problem is this. If we're going to make a function, well, it has to pass the vertical line test. So here's some random vertical line. It intersects more than once, which means fail, not a function. So we need to start doing domain restrictions. So if we set this as our domain restriction, then we actually miss out on part of the, or we still face this problem. So we gotta actually chop our u's in half. So I would just keep that on. So if we make this restriction here, and we just keep this half and this half, we now can pass the vertical line test. So let's see here. That is how we will define it. And actually we cannot include the pi over 2. Alright. So that is actually going to be our new range. So for Arcsecant, just to state from our graph here, our x values, or I should say our inputs, right? Our inputs will be from all positive values greater or equal to 1 here, and it will have to be less than all values from negative 1. So let's see here. We have a domain. So we'll write it in interval notation. Oops. So from negative infinity to negative 1, union with 1 to infinity. And the range is going to be from, let's see here, 0, we want a square bracket, to pi over 2, union with pi over 2 to pi. Alright, so why are we excluding the pi over 2? The reason why is this. Arcsecant cannot give you a pi over 2 as a value. So Arcsecant of some value, the claim is it cannot give you a pi over 2. The reason why is, think of it this way. If we have secant of pi over 2, that is the same thing as 1 over cosine of pi over 2, which is 1 over 0. That right there is a problem. So, since pi over 2 is not inside the range, or is not inside the range of secant, or I mean, no, since it's not in the domain of secant, then it cannot be in the range of arcsecant. And that's where that is coming from. The domain, if we recall, that is all the, you think of the domain for arcsecant, that it has to be all the valid y values, the range of sine or secant. So when we think about secant, when you plug in any value, we saw those nice u's. So here's our u's. Well, these include all values except what's in between 1 and -1, which is why for our domain here, we have to exclude those values between -1 and 1. So that is arcsecant. Arccosecant is not really that interesting once we look at arcsecant, because it's pretty much the same story, except we have to shift all the graphs over a little bit. So here is, well, y equals secant, oops, that was funny, but no. And x equals cosecant y. So you can see how they're just a shift up from each other. So our range restrictions are actually going to be pretty much the same, just shifted over a little bit. And we'll still have the same domain. Alright. So that was arcsecant. Here's arccosecant. Now, here we go. So x equals cosecant y. This will have a domain from -infinity to 1. And I just made the same mistake again. That's hilarious, exact same spot. Union with from 1 to infinity. And as we saw, the range is going to have a shift over. So we're going to restrict the range from -pi/2 to 0, union with 0 to pi/2. And the reason is because if we think of secant itself, secant of 0 is the same thing as 1 over sine of 0, which is 1 over 0. So that's why we have to exclude the 0 from the range of arcsecant or arccosecant. Alright, so we got domains and ranges for arcsecant and arccosecant. Arccotangent is going to be very similar to arctangent. So let's go ahead and get those on the board, or I mean on the Desmos. So here's arctangent, and here's what arccotangent looks like. And it's pretty much a way of just going in the opposite direction, which is kind of what we should expect for recall the graph. So here's tangent x, and here is cotangent x. Notice how they're kind of opposite here, so it should be no surprise if they're opposite for the inverses. Alright, so as we can see here, we have to restrict the range again. And so for arccotangent, we're going to restrict the range in the following manner. So arccotangent. Now, arccotangent or cotangent itself had a domain of all real numbers. So, or I mean, it had a range of all real numbers. So the domain for arccotangent is all real numbers. And so for range for arccotangent, we're going to restrict it between 0 and, oops, we need to actually delete that. between 0 and pi. There we go. So we cannot include the endpoints 0 or pi because cotangent itself is equal to cosine over sine. Well, sine of either 0 or pi is 0, so you get a number divided by 0, which is why we have to exclude those. So that's the three trig functions in brief. I'm not going to develop much more than that. It was just kind of to show you what's going on in the grand scheme. If you want to dive more into nitty gritty, you can always just make a table of values and see where those graphs come from. And so to put the final touch on this video, what we'll do is just look at what arcsecant x looks like. There's arccosecant x. So these functions here differ from what I was doing before, where x equals secant y. That's because these have the built-in domain restrictions that we were just going over. So here's arcsecant, arccosecant looking very similar there. And then here is our arccotangent. Alright. That concludes our video. Thank you for watching. If you've been enjoying our content, please subscribe. Consider supporting us on Patreon. Thank you for joining our math party, and I will see you next time.